Welcome to the Deep Dive. Today we are tackling something pretty deep, sits right on the edge where solid physics meets some really, let's say, speculative but beautiful math.
Yeah, it's a great one.
Our mission for you listening is to unpack this question. Is the Higgs field, the thing giving particles mass, just a complex scalar? Or could it have maybe an octonionic origin?
And it's a really important question because, look, the standard model works incredibly well, right? But it does feel a bit cobbled together sometimes.
Just postulated.
Exactly. It's built on this cis-U3 times SU2 times U1 symmetry group that covers your strong, weak, and electromagnetic forces. But why that group? That's where people start looking for deeper structures, like the four-normed division algebras.
Right, the building blocks, real numbers, complex numbers, quaternions.
And the really strange ones, the Octanions, Math BBA and Math BBA.
Okay, so let's get the sort of textbook answer out first. Inside the standard model we actually use, what is the Higgs?
Right. So definitively, no ambiguity here. It's a complex scalar field. Not just complex, it's actually a complex doublet under the weak isospin group SU2
And why complex? Why are complex numbers, math BBC, so essential there?
It comes down to interactions. The Higgs needs to interact with both the weak force, that's SU$, and it needs to carry weak hypercharge under one Y$ particle. That's basically the group of phase rotations. Think of rotating something on a 2D plane.
Like on an Argand diagram.
Exactly. And you need complex numbers for that kind of phase rotation math to work. It's baked into how we unify the electromagnetic and weak forces. Reals are too simple. Quaternions cause other issues. It has to be complex.
So the complex nature is locked in by observation, by the forces we see. Given that, what's the fundamental mathematical reason the Octanions just don't work for the Higgs itself?
It's a showstopper property, non-associativity. We know quaternions are non-commutative, right? Stubby times boogie isn't baller times to Bible. Octonions are non-commutative and non-associative.
Meaning the order you group multiplications matters. Like the AC.B.C. is actually different from a C.B.C.
Precisely. And that breaks everything we build quantum field theory on.
Because QFT relies entirely on associativity. For operators, for how symmetries combine.
The whole structure, Lie groups, which define our fundamental forces, need associativity. So within the physics framework that found the Higgs boson, the answer is a clear, definite no. The Higgs field, as we know it and measure it, cannot be octonionic.
Okay, definitive answer, no. But, and this is where it gets really cool for you listening, just because the Higgs particle isn't octonionic doesn't mean the whole structure of the standard model didn't somehow emerge from octonions.
That's the speculative leap. It's this idea that maybe the very weirdness of octonions, their non-associativity, is precisely what constrains reality into the form we see.
How does that work? What are people looking at?
Well, a lot of the research focuses on things like the exceptional Jordan algebra, often denoted mathfrak, though.
Whoa, okay. Break that down a bit. Jordan algebra.
Think of it like a special kind of 3x3 matrix, but the entries, the numbers inside, are octonions, and it has its own peculiar multiplication rule.
Okay, a 3x3 grid of octonions.
Yeah.
What does that represent physically?
It's proposed as the underlying mathematical structure, and here's the kicker. You look at the symmetries of this object, the ways you can transform it while preserving its structure. That symmetry group turns out to be another exceptional object, the Lie group 4,4-Herfurate.
443, right, heard of that one.
And amazingly, 4443 contains naturally the exact standard model gauge group, SESI3 times SU2 times U1, well, technically divided by a math to 66. But that's the right structure.
So instead of just picking the standard model group out of thin air,
it derives it. It falls out of this deeper octonionic algebra that's incredibly appealing.
And what about the Higgs in these models? Is it just added in again?
No, that's another beautiful part. It often emerges from the structure. For example, in some models, like Colfuri's work, you get something Higgs-like emerging from what's called quaternionic triality.
Triality. Is that related to the three generations of particles?
Exactly. It potentially explains why we have 3 copies of everything, electron, mu, and tau, and so on. In other approaches, the Higgs appears as part of a larger mathematical object, like a superconnection. And you can even try to calculate things like the ratio of the Higgs mass to the W boson mass.
Okay, so these octonionic models sound amazing. They explain the particle families, the charges, the forces, the whole kinematics, right? The structure.
Yes, the structural elegance is undeniable.
But what's the big problem? Why isn't this mainstream tested physics yet?
The massive hurdle is dynamics, how things interact and change over time.
Wow.
We don't have a working Lagrangian for these theories yet. That's the master equation describing energy and motion in QFT. And because of the non-associativity, we don't know how to reliably calculate scattering amplitudes, what happens when particles collide.
So you can't make concrete predictions to test against experiments like the LHC.
Not yet. We can't bridge the gap between this beautiful mathematical structure and quantitative experimental physics. That's the challenge.
So let's summarize for everyone. The Higgs field we've found. It's definitely complex, no question within standard physics.
Correct.
But the Octanions might be hiding underneath, providing the reason why the standard model looks the way it does, why it has that specific SU2 times SU1 structure, maybe even why there are 3 generations.
It's a tantalizing possibility. This whole line of research really forces us physicists to question one of our most basic assumptions: associativity.
Right.
And for these Octonionic ideas to move from mathematical elegance to actual predictive physics, we need a breakthrough. We need, somehow, a new principle for dynamics, for how things evolve in a world that might be fundamentally non-associative at its core.
A whole new way of thinking about cause and effect, maybe. That's
Right.
definitely something to chew on.
It really is. It's the frontier.